request Professor Kenichi to please start.
Thank you very much. So this is the last part of my talk. And so today is the climax of my series of talks. So so up to not yesterday, the day before yesterday, I've been talking about the Taichimura metric. So this is one of the metrics which we can define on the Taichimura space. Today, I'd like to consider another kind of metric, which is called the Thurston metric on the Taichimura space. So let me just start with a definition. Thurston's metric. So what was the idea of the Taichimura metric? So you are given two homomorphic Riemann surfaces, so both of which have some complex structures. So the idea of the Taichimura map is to find the most efficient way to deform one complex structure to the other, and we measure how the structure was distorted. And the measure of the distortion was called the dilatation. And so by defining the distance to be the infimum of such a dilatation, then you get the metric. Or the more precisely, it's just the log of the dilatation, then you get the metric. So in that case, what we consider is the complex structures. But instead of that, we can regard the Riemann surface as a hyperbolic surface, so by uniformization theorem. So instead of complex structures, now we consider hyperbolic metrics. On closed surfaces. So by uniformization theorem, so if you have a Riemann surface sigma, we are assuming that the genus is greater than or equal to 2, then its universal cover is the upper half plane. And this sigma is the quotient of the upper half plane by some discrete group, which is called the Fuchsian group. And that is a discrete subgroup of PSL2R. So the group of the conformal automorphisms of upper half plane is equal to PSL2R. That is the group of, this is plus minus. All right, so this is a group of the linear fractional transformations acting on the upper half plane. Okay. So now you can be regarded as a hyperbolic plane. So it's a upper half, there's a model of the upper half plane, and the model of the hyperbolic plane is a upper half plane. It's by considering probably it's the metric like that. Probably I need to put 2 or something, but anyway, so the simplest form should be like that. So just ignore the constant. Then it's this group is the isometry group of this metric. Okay, so then this can be regarded as a hyperbolic surface. That means surface with constant negative curvature. Gamma is the covering translation group. So this is a universal cover of that. So the fundamental group of the sigma acts on U as a covering translation group. And the gamma is so that group, covering translation group. Okay. So now another way to define Teichmüller space is this. So that we consider the pair where the sigma is a hyperbolic surface and F is a homeomorphism. And we mod it out by some relation. The two pair, as before, two pairs, sigma 1 and sigma 1 F1 and sigma 2 F2, related by this tilde when there exists an isometry. Well, probably it's better to say orientation preserving isometry. Well, probably if you yeah, it's better to put the orientation preserving not here, but probably here. So it's an orientation preserving. So sigma, so we assume we orient U and we that induces orientation of sigma. So then there exists. So if there exists an isometry from sigma 1 to sigma 2, homotopic to the composition of F2 and F1 nimbus as before, then they are regarded as a single point. Then this is the same as the previous definition if we consider this uniformization theorem. Okay. So now, because we are now considering the deformation of a hyperbolic metric rather than deformation of complex structure, this definition is more suited to our argument. Okay, so now let us. So what we'd like to do is, so the aim is to measure the difference of two hyperbolic structures. Okay, so for that, let us remind you of the elementary definition of the Lipschitz constant. So suppose you have two metric spaces, X and Y. And the continuous map from X to Y. Then the Lipschitz constant of the discontinuous map is defined to be supremum of this ratio. So you compare this should have the distance dx and this should have distance dy. So you should compare the distance of the image of 2 points in a y and this one. Okay. So this might be infinity. Okay, but if this is bounded then we say phi is Lipschitz. Lipschitz, is it correct? Lipschitz continuous. Okay. And so instead of the quasi-conformal map, which was used in the Teichmüller metric, we like to use these Lipschitz maps to measure the difference of the two hyperbolic structures. So here is the definition. So you have you have 2 points. We define the distance between them to be the infimum of the Lipschitz constant of G. Oh, sorry, there is a log here. Of G, where G is a homeomorphism, homotopic to the that one. Okay. This should be assumed to be homeomorphism. Homeomorphisms. Okay. So in this definition, we don't know if the infimum can be attained by some map. Okay. This is just the infimum. So so it's a kind of the theorem or lemma that this is achieved by some map. But so as a definition, it's not assumed. So they just take the infimum of the difference of the two hyperbolic structures. And so the first thing we'd like to show is that this is a kind of metric, but it's not a really metric. Let's recall what's the definition of the metric. So the first thing is the number is so that the function, the value of the function is non-negative. And the second is that if the value is 0, then the 2 points are the same. So that's the second. And the third was the symmetricity. Okay. And fourth is triangle inequality. Okay. If the function satisfies these 4 conditions, then it's called a metric. That was the definition. Okay. But here we don't have a symmetricity. This dl is not symmetric. So sometimes we call such a metric asymmetric metric. Asymmetric metric. It's a kind of hard to pronounce, but asymmetric. We sometimes call it such a metric, asymmetric metric. Okay. So the lemma is that the dl is an asymmetric metric. Okay. So it's easy to check the triangle inequality. The easiest one is the triangle inequality, in fact. So the first thing we should remark is that the Lipschitz constant of the composition of two maps is bounded by the product of the Lipschitz constant of the two. So this is easy. So I just so we take a supermem. So if you have two such things, then the supermem of the product is bounded by the product of the supermem. So so this should hold. Okay. And from there, so if you have a 3-point in a Teichmüller space, and maybe let denote it a pair. So then the distance between x1 and x3 is by definition an infimum of the k homotopy to the x3 composed with S1 inverse log Lipschitz k. Okay. So because k is a homeomorphism, it can be decomposed into the composition of the homeomorphism from sigma 1 to sigma 2 and sigma 2 to sigma 3. So this is equal to the infimum of the G homotopic to which should be the G. This should be 1, and H should be the F3, F2 inverse, and the log Lipschitz H composed with G. Okay. But because of this inequality, this should be inf log lip H plus log lip G. Okay. And again, the infimum of the, oh, sorry, it's okay. So again, because of the infimum is bounded by that, so it's somehow something is strange. Oh yeah, it's okay. Yeah. So infimum is taken like that. So that wait a minute. Something strange. So what we'd like to do is take the infimum. Actually, this H and the G might be different. Oh yeah. So they move independently. So this is equal to the inf log lip H plus inf log lip G. So these two can move independently. So we don't care about in general, the inf of plus something is bounded from below by the inf plus inf. But here, these two move independently. So the infimum is the same for these two. So you have such equality. So this should be x1, x2 plus x2, x3. This observation, I use this one. So this should be dip h times dip g, taking log, so it's a log dip h plus log. In the second line, yeah. So every map can be decomposed, every homeomorphism can be decomposed into two. Into the homeomorphism from, so if you have a homeomorphism from sigma 1 to sigma 3, then anything like that can be decomposed into the composition of the two homeomorphisms. So they are the same. So we are considering all the homeomorphisms, so they are the same. Right. So this is okay. That's just computation, but what is not so clear is something like this. This is always greater than or equal to 0, not negative. So you know the Lipschitz constant in general might be less than 1. Then if you take log, it might be negative. Okay? So in general, this might be, so if you just forget everything, then just consider the log of lip, then that might be negative. But here it's impossible, because the area in sigma 1 and the area of sigma 2 are the same. So if you have a Lipschitz map whose constant is less than 1, well, maybe you can approximate it by something differentiable, then calculate the area. Then the area of image must be less than the area of the domain. So, but it's a contradiction because they should be the same. So this is derived from this fact. So the last thing we need to check is if this is 0, and then these two are equal. The proof of this one is just like the proof of the same fact for the Teichmüller metric. So this means there's a sequence of the Lipschitz homeomorphism from sigma 1 to sigma 2 such that the Lipschitz constant converges to 1. And again, then you use the theorem, Ashkori-Altscher. Altscher to get a map with Lipschitz constant 1. The Lipschitz constant 1 means isometry. So then you get, as a limit, you get the isometry. So that's a proof. Right. Okay. Is it clear? Yeah? To here? So this is a metric, but not a usual metric because there's no symmetricity. The DLX1, X2 might be different from DLX2, X1. Okay. So now, what we'd like to see next is an analog of Teichmüller map. So in the case of the Teichmüller metric for given 2 points, there is something called Teichmüller map, which is the most efficient map as a deformation of the metric. So so in that case, the distance is realized by Teichmüller map. So now what we'd like to introduce is something called stretch map, which is an analog of the Teichmüller map in this setting. But for that, we need to define something called geodesic lamination first. Okay, so sigma, so we are considering sigma, which is a hyperbolic surface. So we are already assuming that it's closed and oriented. So a hyperbolic surface. And lambda is a subset, is a closed subset of sigma, is called geodesic lamination. If lambda consists of probably it's lambda is a union of disjoint geodesics. So here, when we say geodesic, it's not a geodesic segment. It's a complete geodesic. It's either closed geodesic or the infinite geodesic, the geodesic which is infinite in both directions. So a typical example of geodesic lamination is something like this. So you take, so this is a hyperbolic surface of genus 2. And so we draw a closed geodesic here, and probably there also. And add infinite geodesic spiraling around here and there. Well, it's probably it's better to make it spiral from the other direction because it's easier to draw. Something like that. So this one spirals around this closed geodesic from this side, and spirals around this closed geodesic from that side. So the union of these three geodesics is a closed set because, this is a closed set, this closed set, and every point lying on the spiraling one should converge to a point after passing to subsequence, it should converge to a point on the closed geodesic. So that means it's a closed set. So the union of these three geodesics is geodesic lamination. This is a very simple example, but there are many. Generically, the picture is much more complicated. So the geodesic, such a geodesic might spiral around itself, or something. There's something called the exceptional minimal set, and the picture is very complicated. But anyway, the definition is something like that. And in particular, what we would like to consider here is something called complete geodesic lamination. So a geodesic lamination lambda is said to be complete when each component of the complement is an ideal triangle. So the meaning is this. So you have a lamination like that. So you just consider the complement of this set. Then it's a hyperbolic surface, but the incomplete hyperbolic surface whose boundary, whose frontier is a point on a geodesic lamination. So you have some hyperbolic surface, but suppose you have so many geodesics, so the maximally, so you put for instance, the typical picture is like this. So you put there, close geodesic there, and cut it out, cut the surface along the closed geodesic, then you get a pair of pants, such a picture with closed geodesic with three boundary components. All of them are closed geodesic. Now you put spiraling geodesics there, as many as possible. One there, probably one there, and one there. Then if you consider the complement of this one, then what you get is something like this. So union of something like this. So this is something called ideal triangle. Ideal triangle is a triangle which you can draw on a hyperbolic plane, and vertices, all the vertices lie on the ideal boundary. So it's something like this, for instance. So this is upper half plane, and take 3 points on the real axis and connect them by geodesics. Then this one is an ideal triangle. So if the complement of the geodesic lamination, each component of the complement of the geodesic lamination is ideal triangle, then that means you cannot put any extra geodesic to it to preserve the condition that it's geodesic lamination. So you cannot add anything more. Then it's called a complete. Okay. So and then for a complete geodesic lamination on sigma, you can define something called a stretch map. So so we are considering the lambda complete geodesic lamination. On a closed hyperbolic surface sigma. Then you can define a stretch map. The stretch map is something. So so for and probably and the constant t greater than or equal to 1. You can define. You can what this is what Thurston defined. So Thurston defined for these two, these three, the stretch map. So you consider the map for on a ideal triangle level. You consider a map. So you have such a picture on ideal triangles. So the same picture here. So you just change the parameter here. So you stretch it. So if this is 1, then here you have t. So you stretch this part by the factor t. Such a map is called a stretch map. So you define, so you take the one constant t and stretch everything by this factor on the complement. Then it can be extended to the entire surface. So you have a map. So probably it depends on lambda and t from sigma to some hyperbolic surface sigma prime. So it's called a stretch map. It's not so easy to show that it's really well defined. So on each either triangle, it's easy to define it, but there's some kind of compatibility to extend the entire surface, and that's not easy. But anyway, so he showed that you can define such a map, and this plays the role of the Taichi-Miller map in the Taichi-Miller metric. So let me state the theorem of Thurston. So in general, you cannot say that for 2 points very far from each other, you can define and you can find a stretch map as in this definition. But locally, it's possible. So every tangent vector of the so you consider some point. So for any point, sigma f in the Taichi-Miller space. So any tangent vector of Taichi-Miller space at that point is represented by an infinitesimal stretch map. That means you consider the stretch map something like that, and its image, and so as a how to put it? It's as a limit of the limit T1. Usually, how to put it? So this is an arc. So this should be the vector corresponding to the derivative of this arc. So that should be. They should know, but probably it's better just to. So the derivative of this, how to write it? Usually, probably d, when t is 1. So you consider the stretch map like that, and then make t go to 1. Then this sigma prime approaches sigma. So you can consider the vector, which is tangent to that arc. So that's this. So that this theorem says for every direction in the Taichi-Miller space, there is a stretch map in that direction. Okay. Yep. Yeah, locally you get it. Locally you get it, but not globally. So So locally you get geodesic by this way. But so what's different from the Taichimura case is it's not globally defined. Now, what we'd like to consider next is cotangent vector. So in the case of Taichimura metric, so the cotangent space was the space of quadratic holomorphic quadratic differential. So in a case there's some other object which correspond to the cotangent vector space. So now we'd like to define something called measured lamination. So we consider lambda, which is a geodesic lamination on S, on sigma, and we consider transverse measure. Transverse, sometimes we could put the invariant measure, positive measure, supported on lambda. So that means, so if you have a lambda locally like that, then for each arc transverse to that, you get some positive number. Okay. And it is invariant with respect to the parallel translation along the leaf. So the measure of this arc is same as the measure of this arc because it can be, it's the without changing, well, maybe it's better to write like that because it looks like it's tangent at this. So this should be like that. So if you translate this arc so that there's no non-transverse intersection, so the picture should be like that, then the value of the measure here and the measure here, the value here are the same. That's the invariance of the transverse measure. So there's the invariant with respect to the parallel translation along the leaves, along lambda. So and when I say it's supported on lambda, then there's no. So if some arc intersects lambda, then the value should be positive, not 0. So if you have such a measure, then the pair, so the transverse measure positive mu, then the pair of the geodesic lamination and the transverse measure is called measured lamination. So, right. So for instance, if you have a disjoint union of closed geodesic like that, then you can put a Dirac measure. So just count intersection, the number of intersection points, then you get a measure. So the Dirac measure is just a Dirac measure on that. Take the sum, and then it's a measure. It's a transverse measure. So it's one of them. No. This is just a lamination, geodesic lamination. I'm not talking about complete geodesic lamination, just a geodesic lamination. Now, this is the space of the measured lamination on sigma. this is space of the measured laminations on the sigma. And we can endow topology on that space, on that set, which is topology coming from, weak topology coming from the measure. So if the measure is closed, then the points are closed. So then what Thurston proved in the 1970s is that this is homeomorphic to the Euclidean space of dimension 6G minus 6. So it's a homeomorphic to a Teichmüller space of S. And what we'd like to consider is the projectivization of this space. So it's so you consider this contains this contains an empty set by definition. So we just take it out, and then identify two measured lamination, one of whose transverse measure is a scalar multiple of the other. Okay, this is the scalar. Then you get something called a projective lamination space. And this should be homeomorphic to the sphere of the dimension 6G minus 7. No, it's a hyperbolic surface. Oh, sorry. This should be sigma. So here's sigma. Now, what I'd like to tell you next is that this PL sigma is embedded in the cotangent space. Okay. So there's a theorem, again by Thurston. So you consider the map like this. So the I haven't talked about the length of the projective lamination or length of measured lamination. For a measured lamination on sigma, you can define its length. So it's just integration of the length function, so along the leaf. So the lambda is a geodesic, so you have a length function. So you have an infinitesimal length function, and you have an infinitesimal measure. So you have a transverse measure, so you can consider the infinitesimal version of the measure. So consider their product and integrate it on the surface. Okay, that's the definition of the length. So it's a natural to define a length like that. For instance, if you consider Dirac measure, the sum of the Dirac measure of the closed geodesic, then the d lambda is just a length function. So so if you have a Dirac measure like that, then the two-dimensional integration of this part is just a length. So the sum. So if you take the entire integration, then it means just a sum of these three lengths. Okay. So it's a natural to define the length of the geodesic lamination or measured lamination like that. So it's just the generalization of the length of the closed geodesic. So in the case of the closed geodesic, we put the Dirac measure as a transverse measure, then you get by this definition, you get exactly the length of that closed geodesic. Okay. Now, the theorem of Thurston is something like that. So we consider d log length PL sigma to cotangent space at the sigma f. This is an embedding of PL sigma to the boundary of a convex body in this cotangent space. So when I talk about convex body, so you need to define some norm on the cotangent space. But there is a natural, so because I don't have enough time, I don't define the norm precisely, but there's a natural way to define the norm, because the tangent space has a natural norm. So that because you know that you have a matrix. So you have as an infinitesimal version of the curve, as a derivative of the curve, you have a norm on the tangent space. So because cotangent space is just a dual of the tangent space, you consider the vectors whose norm is equal to 1, and then take the the supremum of the pairing, then you get the norm on the cotangent space. So that's the usual definition of the norm on the cotangent space. And then with respect to that norm, length function is well defined on the major lamination. But the length function is not well defined on the projective lamination space, because you are identifying two scalar multiples. But if you consider the log of the length, so the d of the log of length is equal to the length, d length divided by length. So if you put a scalar here, it's cancelled with the scalar here. So that this is well defined on the projective lamination space. So what's important is that one is the injectivity of this map and the convexity of the image. So it's not so easy to show. But anyway, so it's proved by Thurston. And if you are interested in this topic, so what you have to read is Thurston's paper, minimal stretch map, so which is not published in any journal. But you can find it in archive as a preprint. Now, I can now at last state our theorem. So this theorem is the collaboration of Yifan and myself and that another. So this is an analog of Royden's infinitesimal rigidity theorem. So the day before yesterday, I just when was it? It probably the day before yesterday. So I talked about Royden's theorem and its infinitesimal version. So this is this corresponds to the infinitesimal version of Royden's theorem. So suppose you have an isometry, the complex linear isometry. No, it's not complex. It's a real. It's any. Well, linear can be dropped probably, but not for the moment. So any linear isometry K from the cotangent space of the Teichmüller space from two cotangent space of another point, the Teichmüller space, is induced by a mapping class group, by a mapping class. Okay, so let me remind you that for the infinitesimal Roydens theorem, you had also the linear isometry between cotangent space. But because at that time we are considering the Teichmüller metric, so although the cotangent space is the same, the norm defined here is quite different. So the norm was induced by Teichmüller metric at that time. But now, so we have a norm coming from the Thurston's asymmetric metric. And then the assumption is the same. So just suppose that you have a linear isometry. Then it comes from the mapping class. So the conclusion is the same. Or maybe conclusion is a bit different because in the case of the Teichmüller map, so there might be some constant, whose absolute value is 1, and this map might be composition of the isometry with this kind of the scalar multiplication. But here there's nothing like that. So it's just it coincides with the action of the mapping class. So the corollary of this infinitesimal version of the of the rigidity with respect to the Thurston metric is rigidity. So the Roydens rigidity is derived from the infinitesimal version. So that this rigidity also is derived from the infinitesimal version. So this is equal to the mapping class. So the proof is quite the same as in the case of Roydens. So if you have such a thing, then you compare these two, and then they take that same the same one point to the same point, and also the tangent. So it acts on a tangent space by the same linear map. Then the direction of the geodesic is the same. So it's just it gives the same isometry. Okay. So, but for this theorem, there was an earlier proof by Walsh. So, but he uses some global geometry of the Thurston metric. So the technique is quite different. So that we show the infinitesimal version first, which is stronger than the rigidity theorem, and then as a corollary, we get the alternative proof of the Walsh theorem. Genus is bigger than 3. So if genus is 2, you have a kernel. So it's 2 to 1 map. But so if genus is greater than 3, and then you get something like that. So so there's no time to talk about the proof of this theorem. So I should stop here. Thank you very much. That's all for my talk.